Welcome student to video lecture 5 PCH 2801 unit 3 organometallic chemistry lecture 5 part 5. In the previous lectures we have discussed the classification of organometallic compounds, hapticity, related classification, then alkene transition metal complexes, alkyne transition metal complexes, allyl transition metal complexes, and now we are going to discuss it regarding 1,3-butadiene metal transition metal complexes in this lecture. I am Dr. Devanga Pandya from Department of Chemistry, St. Xavier's College, Autonomous, Ahmedabad. Butadiene complexes in which the conjugated dienes such as 1,3-butadiene act as 4 electron donor ligand. So allyl act as 1 and 3 electron donor, and here we can see 1,3-butadiene act as 4 electron donor ligand. 1,3-butadiene exists as two conformational isomers which are in rapid and dynamic equilibrium with each other. We have these two kind of isomer of 1,3-butadiene is available, as trans isomers and as sinister cis isomers. This one is in 95% and this one is in 5%, and they are in equilibrium. Now the energy of the S-trans form is 12 kilojoule mole, lower than that of the S-cis form. So the energy of that one is higher. You can see this one is little lower energy, 12 kilojoule mole, lower than that of S, that is S. S is higher, that is 12 kilojoule mole inverse, that much higher energy as cis form has, and as trans form has lower energy, and hence it is stable. You can see here the crowding is that means pi electrocloud is quite closer, and here in opposite directions of stability always been with the trans isomer. Therefore, the equilibrium mixture contains 95% more stable that is transforms, and only 5% stable cis form. Despite of this difference in the stability and abundance, the S-cis form is more suitable conformer of 1,3-butadiene to act as 4 electron donor ligand as a for a metal atom. S-cis form of 1,3-butadiene can be bounded to metal atom in two different ways. So here you can see S-cis form have these two different form, L2 type ligand and LX2 type ligand. We can observe these two type of formation over here. But in both the modes, 1,3-butadiene act as eta 4 and 4 electron donor ligand. Now let's see the method of preparation. First one is the reaction of metal carbonyl with 1,3-butadiene. When a metal carbonyl is treated with 1,3-butadiene, two carbon monoxide ligands are replaced by the diene molecules forming transition metal butadiene complex. Here you can see cis form treating with FeCO5 at a high pressure will going to get these two carbon monoxide is substituted, and will going to get this eta 4 complex of butadiene Fe complex. When a mixture of 1,3-butadiene and FeCO5 is irradiated by UV light, 4 CO ligands are replaced by two molecules of 1,3-butadiene forming a bis, that is eta 4 butadiene complex. Here is the reaction. We can see FeCO5 plus 2 mole of 1,3-butadiene and irradiated by UV light will going to get these two eta 4 ligand are associated with Fe, replacing two carbon monoxide molecule in this reaction. Some other example we can see over here. Cis butadiene isomer will going to treat it with this metal carbonyl, and UV light irradiation will going to give this kind of different what we can say butadiene complex formations by substituting carbon monoxide. The same pattern would be there. In the case of derivatives of 1,3-butadiene, isomerization or rearrangement of diene may occur as we observe over here. Here you can see substituted cis isomer of beta 1,3-butadiene. This one is a trans arrangement of 1,3-butadiene. These two isomers will treated with FeCO5. We're going to get the trans isomer over here, substituting 2 carbon monoxide. Similarly, here tetra substituted 1,3-butadiene is there, treating with the same FeCO5. We're going to get this kind of complex substituting 2 carbon monoxide as well. Now, second reaction in the synthesis or preparation, we can say reaction of metal halide with 1,3-butadiene. Some 1,3-butadiene complexes or 3-butadiene complexes can be prepared by the reactions of metal halide with 1,3-butadiene under suitable condition. Here we have potassium tetrachloroplatinate treated with 1,3-butadiene. We're going to get eta 2 complex of this butadiene. So it's a 3-butadiene complex is going to be formed over here. In this 1,3-butadiene act as a 2 electron donor as a dihaptoligand. So in certain cases, not in all cases, majoritarily it acts as a 4 electron donor, but in certain cases it acts as 2 electron donor dihaptoligand as well. 1,3-butadiene may also act as a bridging ligand, and that we can see in this slide as a bridging ligand. Here you can see 1,3-butadiene act as a bridging ligand with these 2 metal platinum center. So 2 mole of this potassium dipotassium tetrachloroplatinate treated with 1,3-butadiene will going to get this bridging ligand product. Here as a trans form of 1,3-butadiene act as bridging ligand. Early transition metal complexes can be prepared by the reduction of halides in presence of ligand. Here you can see chromium in gaseous form, carbon monoxide in gaseous form, and 1,3-butadiene in gaseous form. We're going to get these complex formations directly. Third process is a metal atom vapor phase synthesis, and in this synthesis the condensation of a vapor of a metal in the presence of 1,3-butadiene and a suitable co-ligand like carbon monoxide or trialkyl phosphine etc. produce the butadiene complex. Here you can see the example: chromium in gaseous form, carbon monoxide in gaseous form, and butadiene in gaseous form as well. The same reaction is going to be obtained. The structure of FeCO3 eta 4 C4H6 is given like this one. Here you can see carbon bond length both the side, equidistance is there. As already we have discussed in allyl metal complexes, when they form, that means tetrahapto, that means all the carbon attached with the ion simultaneously. This dotted line shows that one, and as a result of that, each bond length between carbon distance is going to be equivalent. The ligand 1,3-butadiene is present in a cis configuration. The plane of 4 carbon atoms of 1,3-butadiene is nearly parallel to that of the 3 carbonyl groups. Fe atoms is equidistant from each of the 4 carbon atoms of the diene, and all the CC bonds of the diene are of equal length, that is of 1.45 angstrom, which already we have discussed why it is at 1.45 angstrom distance. This fact suggests a pi complex rather than a complex containing 2 metal carbon sigma bonds. 1,3-butadiene is planar molecule with sp2 hybridization on each carbon atom. So here we are discussing the bonding and structure of that compound. Valence shell electron configuration of carbon atom in 1,3-butadiene is observed like this one, and like allyl, it has one unpaired electron present in it, and sp2 is the hybridization. In each carbon atom forms 3 sigma bonds using 3 hybrid orbitals, which we have seen early in the earlier slide. One singly occupied 2px atomic orbital is left unused on each carbon, like allyl group, which already we have discussed in allyl group in organometallic fourth part, and according much in a similar way, which is perpendicular to the molecular plane, that is in a xy plane. So here you can see the planar arrangement, and px has one unpaired electron that is indicated over here as pz. So 2pz atomic orbital has a perpendicular arrangement of this unpaired electron in the xy plane. These four parallel singly occupied p orbital atomic orbitals take part in the linear combination forming four pi molecular orbital. This is pi typological mistake. So you can see pi formations. These are the two bonding pi molecular orbitals, and these are anti-bonding pi molecular orbitals. So all these four perpendicular unpaired electrons of carbon, each for carbon, will going to form these 4 pi molecular orbitals. Out of these 4 pi molecular orbitals, 2 are bonding pi BMOs and 2 are pi ABMOs. Appropriate combination of the 4 pi molecular orbitals of 1,3-butadiene and metal based orbitals can be used to construct molecular orbitals of transition metal butadiene complexes as shown in this figure. Here you can see the energy increasing, and this is Psi3 and Psi4, and Psi3 Psi4 has this kind of arrangement py, dyz and dxy. That is a pi orbitals, molecular orbitals of the ligand. And these are the another psi1 and psi2, that is anti-bonding, and this one is bonding. And in this bonding we have px, xz, s, pz and dx square. These are the atomic orbitals of metal with a suitable symmetry, and suitable symmetry will going to overlap resulting to bond formation. So psi1 and psi2 are pi molecular orbitals of 1,3-butadiene are involved in the formation of butadiene to metal, that means donation of sigma and pi respectively. Here A refers to sigma and T refers to pi. Similarly, psi3 and psi4, that is antibonding pi orbitals of 1,3-butadiene, are involved in the formation of metal to butadiene, that is back donation, and it's going to form pi and delta bond respectively using back donation. Now the back bonding, the bonding between metal and 1,3-butadiene may be represented using this figure. These three probable arrangement is there, this two arrangement, and this is the hybrid arrangement of these two. When the donation of psi2 into metal orbital is important, the bonding may be represented as structure A, which you can see in the previous slide. If donation of psi1 into metal orbital is important, the bonding may be represented using psi as structure C, that is the hybrid. And you can see that in this example, FeCO3, eta4, C4S6, all the CC bond are equal length, that is of 1.45 angstrom, which we already seen earlier in the slide. Its structure and bonding is close to the structure C, in which pi electron cloud of butadiene is delocalized on the entire butadiene moiety. Now here you can see if the interaction of psi3 metal orbitals is important, the structure and bonding may be represented by structure B, which suggests a shorter C2 C3 distance than the two outer CC distance, that is C1 C2 and C3 C4. Here the example for that, cyclopentadiene, bis cyclopentadiene zirconium eta4 2 3 C4H4 or Me2, that means disubstituted 1,3-butadiene is there, and here while C1 C2 and C3 C4 distance are longer comparative to C2 C3, which is a shorter distance. The zirconium carbon and zirconium carbon 1 and carbon 4 distance are typical of zirconium carbon sigma bond. At the same time, zirconium is farther from C2 C3 than C1 and C4, and hence it is a shorter, C2 and C3 is a shorter one. Therefore B is the main contributor to the structure and bonding of cyclopentadiene 2, that means bis cyclopentadiene zirconium 2,3 dimethyl 1,3-butadiene. Now the properties, this eta4 C4S6 Fe complex is a yellow brown oily compound which is soluble in most of the organic solvents. The coordinated butadiene does not undergo hydrogenation and a Diels-Alder reaction. Electrophilic addition reaction is shown over here in the property. The attack of electrophiles on the coordinated butadiene is less common. However, the following reactions are illustrated, for example, of such electrophilic reaction, which we can see over here. This eta 4 complex treated with HCl we're going to get this positive charge on the 1,3-butadiene, and chloride ionic intermediate is formed, and then it is converted into a Lyle complex, that is a substituted methyl group over here, and chloride is going to associate with Fe, substituting this proton. So we're going to get this kind of resultant allyl complex from 1,3-butadiene. Sometimes the carbocation of electrophile abstracts hydride ion from the saturated carbon atom adjacent to the olefinic carbon atom, extending the conjugation. Here you can see the extension of conjugation with triphenyl carbide carbocation is treated with this compound. So we're going to get this kind of intermediate treating with triphenyl compound. Then this one is the another example where the hydride is going to be shifted from the saturated carbon to adjacent another carbon atom, and we're going to get these two kind of complex formation. Second is the nucleophilic attack. The coordinated butadiene is readily attacked by a variety of nucleophiles such as this. We can see here the palladium complex is treated with sodium methoxide, and we're going to get the substitution of methoxide group over here, converting the butadiene complex into a Lyle complex. The addition of nucleophiles to butadiene saturates the olefinic carbon atom and thus remove it from the conjugation. Here that reaction is shown over here. This is cyclopentadiene, bis-cyclopentadiene complex treated with 1,3-butadiene, and we can see the substitution of one of the carbon monoxide, and a Lyle complex is going to be observed over here. The nucleophile may also attack on the metal atom. You can see nucleophile is going to attack on metal side. Substituting this 2 chloride, we're going to get 2 methyl group over here. Displacement reaction. The coordinated 1,3-butadiene molecule can be displaced by other neutral ligands such as triphenyl phosphine. So here you can see treating with 2 mole of triphenyl phosphine, this complex we're going to substitute this 1,3-butadiene, and we're going to get this complex formation substituting 1,3-butadiene. Well, thank you very much. This is enough from my side. Thank you for paying attention to this video lecture. Keep asking questions. As you know, asking question is a beautiful way to gain knowledge. Thank you.